Hello. Okay, I'm starting the live streams. I hope you guys can hear me better. Mm. Okay, this is basically uh, you know, a group study. So I'll be discussing fewer topics, starting off with what deep learning is, and our main framework would be PyTorch. But we're gonna go deep into what exactly PyTorch is and how you can leverage to create your own models, how uh, the internal workings of the PyTorch is, basic tensor functions, what kind of mathematics is needed, the theory plus everything. Hopefully, this is gonna be something very interactive, and I will also be like debugging and stuff. So the code that I write, I will try to debug is on go, so that you can also see what kind of a you know process you have to go through to build a model or maybe understand the mathematics behind the deep learning, right? Okay, so let's start. Can someone is there any viewer who can just join in and let me know if how the audio and the visuals are? Okay. Anyways, I'm gonna start. So basically, what deep learning is a very, very, very simple definition would be you are trying to find a in traditional what do you say machine learning. You have some data, you wanna build on that data a model, right? You have statistical models that can be used to learn the patterns in the data. But what deep learning, how it's different from a classical machine learning, is that it can actually find the function that can map the input to the output. So your input might be some mostly numbers, right? Anything that can be converted to numbers can be used in a deep learning uh, architecture and be trained on, right? So what you have here is a simple words. You have a input, you want output out of it, for example classification or something, and what you essentially do is create try to find that function that could do that instead of explicitly coding it, explicitly creating a statistical model on that. You rather just create one uh, deep neural network which will find that function for you. Okay, so at the heart, at the core of all this deep learning is linear algebra and calculus and tensor operations. What are tensor operations? It's basically like NumPy. You have had experience with NumPy, I suppose. So it's just numbers and arrays and vectors that you matrices that you play with. You do all kinds of linear operations on them and use all the tools that you have in linear algebra, right? So basically, the first part what we're going to do here is to understand tensors, maybe understand what are tensors in the first place, why are they important, what kind of operations can we do using PyTorch. There are over 300 operations, I suppose, that are in PyTorch, and even more than that. So a lot of things are there, but mostly we're gonna use like a few of them to do most of our work. So let's get straight into the basic mathematics of what tensors are. Okay, so firstly, tensors are a general term for an array of numbers. Now, this array can be 1D, 2D, 3D, 4D, whatever, right? For example, in Python, we have lists, right? So now NumPy also has their own arrays, but tensors are just like NumPys, but they are optimized to work on GPUs. So whenever we are doing deep learning, we mostly works with tensors. Okay, that are provided by PyTorch or any other libraries like TensorFlow or Tensors or something. Okay, so let's start with the first thing, that is a zero rank tensor. What is a zero rank tensor? Okay, zero rank tensor is nothing but scalar, any scalar value. So 3.0.3 is a scalar value, right? X is equals to 0.3. It's a scalar value. It's just one value, and it does not have any dimensions as of. That's why we give zero rank tensors. Okay, then comes in one rank tensor. The tensor with one rank. Here we have one dimensionality, that is along one, an array. So in linear algebra, it would be an vector. So in books, you might find that vectors are notated like this, something 0 point, something like this, right? So these are one rank tensors. Okay, rank one tensor, what do you want to call it, and then a tensor of rank 2, that would be a matrix, right? A matrix, we have had experience with matrix a lot, right? It's just a bunch of numbers here. This is a matrix, but in books you might find that this matrix are denoted by a bolded X. Whatever letter they are using, they will bold it, and then use it. So X would be like, so this would be a matrix. It's a vector. This is a scalar. And coming on to the next part, that is the 3D vector. 3D tensor, right? Tensor with a rank of 3. Okay. Now, here is where things get interesting. I mean, for 0, we have a named scalar, and then it's a vector, then it's a matrix. But starting on from 3D, we don't have any name. We just call them 3D tensors or something, right? So it can be basically, let me show you how it actually looks in the core or something. So you have, let's think of this one. Let's take the same example. Okay. And one more. Now this would be a 3D tensor. What it essentially is basically, I would also like to show you one more thing that starts from here. Basically, what it says, the shape of the tensors. It can also be seen for x dot shape. If you put that out, it will give you a value called 3 comma. That's it. This one, because it has 3 elements in their vector, right? It's just 1D vector. It's just output 3 comma. If you take this one, it will output there are 2 columns. See, 2 columns and 2 rows, right? So 2 comma 2, 2 rows and 2 columns. These are rows and this is column. Okay. Now coming here, we have its shape would be 2 comma 2 comma 2. So what it essentially means in simpler term is that we have 2 matrices. So this is one matrix here. If I can just highlight that part a little bit. Can I use this? This is one matrix here, and then this is another matrix here. Okay, so this whole part would be one matrix combining blah blah blah, and this whole part be another matrix. So it says there are 2 matrices of size 2 by 2. If there were 3 of them, it would be 3 comma 2 comma 2, right? I hope that made sense. Now coming to higher dimensions. So till 3 dimensions we can even visualize and stuff, right? But going beyond this would be much harder. It will be like saying 4D tensors, like rank, sorry, rank 4 rank tensors, right? Now things get really interesting. I mean, now you already have this. What if I have another way to represent this? Okay, think of this as, now this is one, think of it as one straight line. Okay, so this is a point, think of it as a point, right? This is a damn point. This one is a straight line. This is a 2D, so it's basically 2D, right? So it can be a square matrix like this. Visual, I'm just giving a visualization to the whole thing. Now next thing would be, it's a 3D thing, right? So it will be a cuboid or something. It's a stack of something. But now coming to this part, the rank 4D, it's very hard to visualize. First, let's write how it looks in the code. So if we take the same thing and replicate it again, 1, 2, 3, 4, of course, 4 of them are gonna be there anyhow. I'm just putting 0, 0, okay? 0, 0, 0, 0. Right? Now, coming more to the next part, that is 0, 0, 0, 0. Okay, this is done. Then again, starts with the next one. Basically, mm, so now this would how a basic 4 rank tensor would look like, rank 4. Okay, so if we can distinguish between this is, so think of this as, you see, start from here and here there are, if I write out the shape of this, it would be like uh 2 comma 2 comma 2 comma 2, right? Does that make sense? Basically you have, if you check this out, you have 2 columns, okay, then 2 rows in one of the matrix, okay, then you have in this matrix, in this one, you have again 2 of these columns, or 2, and then for the bigger one you have another, this one and this one, so there's 2. That is how basically it works. uh, I know it's kind of confusing, even sometimes I get confused with the whole basic writing, how it's exactly working and all. So that's fine. We will see it in the code anyways. But one way to visualize it is, uh, so as I said, it's a point. Let's say it's a line. It's a plane. It's a 3D cuboid. But once we go beyond this, there's no way to visualize 3D. So what I do is, in tensors, say this whole thing again becomes a dot. You're starting, okay. This thing again becomes a dot, right? So now this is 4D. If I were to say 5D or something, 5D tensors, I can type in this one and add, this is another 1 point, so now it's essentially 0. And if I add one of those squares again here, it will become 5D. If I were to go 6D tensors, now if I add another dimension to these 2 points here and here, this becomes 6D. And if now if I go even further, 7D or something, and we are not going to work with 7D anyways, but still a visualization, so it will be like this and some piche like this, like a cuboid, so it will become like a cuboid. So this is basically a line. This is basically again becoming, uh, what do you say, a plane. So what I'm doing is taking this and projecting it to a single point. So all these points are basically a 4D tensors. You see? So it becomes very, very large, very, very fast. And now I hope you have a kind of idea about how to understand tensors in a sense, or maybe visualize it in some way. Now starting again, let's go and see the actual applications of this tensor. Why are they needed? I mean, in the first place, right? Why do you really need a tensor in the first place? Now we have, let's say some practical example. Okay, you have an image. Image can be uh, like this is the image, right? Now this is, let's say, 28 into 28 pixels. Pixels in the sense these, there are 20 squares boxes, and all these, this is a black and white image. Okay, black and white image, and this value can go from 0 to 1, 0 being the dark and 1 being the light one. Okay, so here it can 0.2, which means it's kind of dark. There's another box is 0.8, it's kind of bright. So what essentially we have is a data that is 28 by 28 in its size. So you have 28 columns and basically a matrix, right? So this is how we would represent an image. Cool. But this is just a black and white, which does not have any other, just it's a 0 to 1, so it's okay. But what if you have a colored image? How would you rather represent that in a tensor? So in that case, what we have here is, we can, most colorful images are RGB, R and G in B, right? So the combination of three can create any color. So let's say 60% of this, 30% of this, and 1% of blue. So 60% of red, 30% of green, and 1% of blue will create some color. So what we have here is again three numbers denoting three different values for a single image. Okay, so you can think of this as this one image that can be decomposed into three different. So this will be a R channel, this is your G channel, this is your B channel. So RGB. So now every pixel here, for example, this is a pixel, right? It can have 0.6, 0.3, 0.1, and basically if you add all these colors up, it we will get the resultant color of that image. So what we have here is a way to represent a colored image, and how this tensor will change, which was just a 2 by basically a 2D tensor, it will become a 3D tensor, because one more information has to be added. So here in this case it will be 3 comma 28 comma 28. This would be the size of the tensor. This is the shape. Here this was the shape, and we were just working with a black and white image, right? So we were able to uh, you know represent a colored image using a 3D tensor coming in. So basically what it's saying is there are three 28 by 28 matrices. So you see there are three 28 by 28 matrix, right? That's it. Now again, what if you have more than one image? There can be 2 3 images or something, right? It does not have to be just one image. You have image 1, image 2, image 3, all of them colored and stuff. Let's say I have 4 images, such that I want to represent them at once. So we have a simple, just add one more dimension, so then it will become a 4D. So it will be like 4 comma 3 comma 28 comma 28. So now I'm able to represent four images, and of basically of 2 3 channels, and 2 by 2 is the pixel of that image, right? So I was able to represent 4 images all at once using a 4D tensor, and this is what you will use. Okay, so what happens is when you do training and all for any models, you don't really put one image at a time. You take a bunch of images. So that's what we call, that's why we call this parameter, this here. We mostly equate this as a batch. Okay. And then this is the channels, RGB channel. So it will see, this is the height and this is the width. So height and a width. You will see this a lot. There as another representation of B, H, W, and C. This is also a way to write it. I mean, the people represent it this way as well, but I like this one. I think PyTorch also use the same notation. Okay, so I hope this part made sense. Why are these tensor important? It's basically a way to represent complex data, a lot of data at once, you know, and use it for training. So when you put on like a batch of 32 images at once, so you will have so now if there's a really good image like 1080 by 1080 or something, it's very hard to work, to be frank. It's a lot of numbers there, right? So you have 32 images of such things, so you have a tensor that would be 32. The shape is 32 comma 3 channels 1080 by 1080. One more example. Okay, I guess that clears this thing up. Let's jump to the next one. Okay, now jumping to the next situation, that is NLP. How text are represented in NLP. And so basically here we have a very simple idea. You have a text, let's say you have a sentence, and the sentence can be, this is a live stream. Okay, this is a big sentence. Now firstly you take tokens. So tokens would be, in this case we are just not doing any subword tokens or something like that. Just think of every word as one token. So this is token number 1, 2, 3, 4, 5. Okay, now in NLP we take the embeddings of all these things. What essentially that means is we project this one sentence into a big vector. So this will be a one vector, this will be another vector, another vector, this will be another vector, this will be another vector, and these vectors are very big. These are called embeddings of that words, right? So this can be a vector of, let's say size would be uh, blah 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 512, something like that. Okay, so now how can I represent this whole sentence in one matrix? It's very simple, right? So you have 5 words, so all you have to do is align them, all these vectors, into 5 of these words. So that's how easy it is. So it will be 5 comma 512, 5 comma 512, right? 5 comma 512. I hope that makes sense. Now what if you have a bunch of sentences again, right? There can be another sentence, there can be another sentence, there are 3 sentences or something. Then again the concept of batch comes in. You have, if this is the what do you say, shape of one sentence, then if because assuming all the sentences are having 5 words inside them, then you would have a batch of, let's say, 3, and every sentence has 5, right? Give me a second, I'll be back. Okay, sorry for the interruption. Starting off again. So where were we? Basically we had, so there are 3 sentences, of every sentence has 5 words, and every word has been embedded into a vector of 512. So this is how you will represent a text in NLP. Okay, I hope now you have a clear understanding what tensors are, how and why we need them, and how do we represent different kind of data. So there can be also videos, right? There can be videos or something. So videos basically are bunch of photos that flows really really fast, right? If you have 60 fps or something, that is basically saying uh, 60 frames per second. I have 60 photos that are coming in per second. So if I were to say image is of 3 and every image is of 1080 by 1080, let's say. So if I had one more column, that would be something like a time factor comes into it, let's say. I can represent that too. Now this representation is something that the engineer or the scientist, they themselves create, that how I want it to be embedded into my whole system. So it can be like the first second this image is coming, the second or first microsecond, whatever, this image is coming in, these are the images that are coming in, right? So now it all depends upon kind the use case that you are having, and what kind of a representation you want from your tensors, right? I hope that made sense. Okay, coming back to the point that we are keeping here is these are tensors, and now we are gonna go and do a lot of operations on these, create them, do operation in the sense just math arithmetic operations, and few functions that PyTorch provides us, which you can directly use to build something out of it. Okay, I hope everything's clear, and I am also being clear. Okay, let's start. We are heading to the code. So these are few things that I was working on. So we are not gonna use any of these for now. Let's just do one thing. Okay, so you have to basically install Torch. That's basically PyTorch. PyTorch is Torch was actual a framework that was built in some other language. Then it was adapted for a Python. So the actual name stays Torch only. Okay. So this is the way you can create a tensor. There are other ways to create tensors as well, but this is the most common way to create tensors. So I'm gonna use that. So you have one tensor here. Okay. I'm keeping. Okay, let's see. If I run this, okay, you have a tensor here. I'm gonna create a lot more cells over here. Okay. A. So A would look something like that, right? Okay. Let's start off with basic operations like addition, subtractions, or something. Okay. So I'm gonna create one simple two of these, and let's do addition of that, right? You have that. You're gonna do additions of both of them. You have the output already given. So this is basically adding a element wise addition. So every element is been added with each other. So you can see these elements are added with each other. Okay. So now the same thing can be subtractions and additions. And there are two ways already. You can see PyTorch has an addition, and you can directly do it with the operator, right? So same thing goes with subtraction and multiplication and division, all that same thing. Now all the operation that you have in Python, for example, let's see this one. This will basically take a square or something, right? Now you see it took a square of something. What it did is, now this can be a little interesting. So mostly it does everything element wise, right? All the things that are happening element wise. Here in this case, we have, let's jot it down a little bit so that we have better understanding on this one. Okay, hopefully I can put it here. Here. Okay, so it says it's 2. Let's put it in a box so we don't confuse it with the shape, right? Then another one is 3 comma 2 comma 3. Cool. Now it says a asterisk b, which is basically take the a of b. So what it's doing in basic, it's, if you think about it, you say 2 3 and 4, and I want to project it. This is this other one, 3 comma 2 comma 3. So basically it's taking 2 to the power 3, 3 to the power 2, 3 to the power 4, sorry, 4 to the power 3, 4 to the power 3, so 3 to the power 8, that is 9, this is 64. So I hope that made sense. Where did this come from? Okay, so that would be the exponent operator. And we are gonna go again. There are few things that can be, done in place basically changes the original uh, array or original tensor in itself. So this is how the in place is done. So here the original one will be appended, original one will be changed. Give me a second. Okay, sorry for that. Yeah, um we have this, seems to be some kind of a problem with the third one. uh, let's forget about that for now. What you exactly have is you're changing the original uh, data point, original tensors in this case. Desired output typing long. Okay, this is probably because of the, mostly it works with floats, so there has uh, some kind of a problem. It has to be float, then this might work actually. Let's debug this. Actually, you can just put point, that will also work, but okay, for better readability, I guess. So now that works. So it was integers. So division does not work with integers, especially when the division is not. Um, it doesn't give an integer, output. Okay, coming to the next part. Um, Here we have something. Okay, let's get to the next kind of operators that we have. Is basically like trigonometry operation that you can do. I'll just give one example that will do it. Okay. You can see this. This is a basic sine function. You are creating the x as linspace is basically what you're creating is from 0 to this value. I want 100 values that are equally spaced, and then you put in the values and you see these are the one you see it's 0.99, and because of the precision problems, it cannot be very precise and all. That's why. That's all good. So this is basic stuff. Having trigonometric operations in your hands are cool. Although I never really used it. Then let's go to exponentials and what they are. Okay, exponentials. Let's try with this one. This seems interesting. Okay, did I do a lot of? Yeah. I think you already know what exponentials are. I don't need to tell you that. Mm. So we have here basically, as I said, linspace, what it does is creates an array that has values from -5 to 5, and the number of, what do you say, equal divisions between them. So it will be like, you see, 1 2 3 4 5 6 7 8 9 10 11. 11 of them are there and they're equally spaced. Okay, so what you do is simple. If you do y of torch exponential of x, what it simply does is it takes, I'm gonna give an example that is much easier to digest, I suppose. You have, let's say this 2 3 4 or something, a tensor like that. When you put it in exponential, you need to understand every operation is happening on a vector here in this scenario, right? The x is actually a vector. It's a big time vector. If I print out the x in itself, oh sorry, autocomplete is too good. Now see, it's a vector. It's a basic tensor. So what it's doing is, if you take the tensors, if I'm just assuming this is our tensor for now, and you have e to the power 2, e to the power 3, e to the power 4, whatever the value is, that's what you are getting actually from exponential. So a single function is able to work on individual elements inside a tensor. That is very important to understand, that these functions are able to do this operation right inside, goes inside the tensor, do all these things on the tensor itself, on every single value independently. Okay, uh, I hope that made sense. Okay, by the way, e's value is like 2.17 or something. I don't remember exactly. 2.17, we all know what e is, right? Isn't not a big deal. Then coming to the next part, that is logarithm, the basic opposite of this. And we have logarithms. It has the same function. It does the same thing. Nothing spooky, nothing crazy here happening. 1 2 3 10 and all that stuff, and you are putting a log on that. So again, working on individual, not like every single element is a tensor. It's not working. The function can go inside the tensor and working on individually. So it's basically saying log of 1, then log of 2, log of 10 or something, and log of 100. So log of 10 would be 1. Sorry, no, sorry. Log of 10 here is 2. Log of, it's actually a natural log, that's why. Okay, if it was base 10, it would be 1 and this would be 2 or something. So I think I have example of that too, base 10. Let's get there. So this is a log of base 10. All right, log of base 10. Oh, sorry. Okay, 10 blah blah blah. I think that is pretty self-explanatory. Now log of base 2 is also there. You can deal with that, not a big deal. Uh, let's see this one. Okay, putting in more cells, rounding it off. Rounding it off. How can you round off the values? Right inside the tensor, each elements. Okay. I don't think I need to tell you what rounding off is, right? It's doing its job basically. Yeah. Okay. And then there is a thing called flow. There's a thing called uh, ceiling, floors and ceilings. Basically takes the I think you know what for the ceiling, and we won't be using it that much. I have my notes prepared actually. I can share that notes with you as well if you do in the description. Let's say something much nicer. Okay, let's say clamp. What is clamp? I've seen people using it. You know, What is clamp? Uh, okay, clamp is 1.2, 1.2. So here what I'm saying is I'm clamping the value between 1 to 4. Any value, sorry, it's basically 0 to 4, right? Any value that goes beyond this uh, threshold 0 and 4, I will make it 0. For example, in this case, in this scenario, we have simple. Okay, okay. Okay, in this scenario, we have 1.2, then 2.7, minus 3.4, 4.9, minus 5.6, and the range is 4. Okay, so in the number line, it would be like 0, and this would be 4. This one lies inside this range. This one lies inside this range. This one lies here somewhere. This one lies here somewhere. This one lies here somewhere. Right? So all those who are near them, I will make them 0. This one will become 4. So what you exactly see is that. See, it becomes 0 and 0, and this one become 4. That is clamping. Cool. Okay. Now let's start comparison. Comparison operators. Comparison. Let's do some basic comparisons of any tensors and how they work. Most of the things work element wise. Okay, everything that we are doing is working on the elements or the numbers inside the tensor. It's really important to understand what is this. What does this do? As I said, it works element wise. Let's see. Again, this is working element wise. What it's doing is checking the elements inside the tensor if they are equal to the other ones. Let's say if we change the like floating point or something, will it be same? Yeah, it's still the same. That's pretty good. uh, okay, coming in. So now this is is it equal to or something, equal to operator? There is not equal to operator. There is greater than, um, less than or something. So all that operators will be present in the documentation. You can check that out, or I am anyway providing the notes, so you can check that out there itself. Okay, now coming to the part where things get a little more interesting, that is reduction operators. Now here we are seeing we have done some element wise operations. We have done exponentials and maybe taking square of something, and pretty cool stuff, right? And then let's go and let's see how summing happens, right? Let's sum a few things. Adding, this is a tensor, we are adding it. Simply what we are getting is addition of every single element inside that 2D tensor. If it was 3D tensor, it will also do the same thing, taking all the elements and just adding it up. Nothing crazy happening here. Now, what if you had a situation where you wanted the sum of the first row, sum of the second row, or sum of the first column or the second column, these two. Okay, in that scenario, PyTorch already has something called as dimensions, where you can set the dimensions along which you want the operation to be performed. And here it's very important, I am telling you, because every model that you create is going to have these things inside them, and to work with them would be, if you know how it works, it will be very easier for you to imagine what's happening. And adding along one row that happens more often than you think. You might think, doing softmax on the output, on the logit output, your stuff, mostly we are summing over the column, right? So this is what I'm talking about, sum along a specific dimension. So dimension number one. So if you say this dude is actually, a 2D one, right? It's a 2D tensor. It is basically 2 comma 3, right? There are two rows and two columns, so it's 1 2 3 5 4 5 6. This is the tensor, sorry, this is a tensor or matrix, whatever you want to call it. And this is your row number 1, row number 2, column number 1, column number 2, column number 3, right? Now, what essentially we have here is I'm asking, so if you take the dimension of something, this one will be 0 and this will be the first. Okay. I'm seeing dimension as 1. So what I'm saying is add along the columns. Add, it's very important, this words, add along the column. So it will add along the column and just give addition of this in one as one scalar and then this as another scalar. So if you check it out, you have the addition of one scalar and second scalar. One thing also you need to understand and keep in mind is that it reduces the dimensionality. It was a 2D tensor, right? It became 1D tensor. There is a tool that says that can keep, if we see here, uh, keep dim equals to true. If you do this, keep dim equals to true, it will keep the dimensions as it is, which is needed actually when you do deep learning. You don't want your dimensions to change. That's important. As the network flows, you really don't want your dimensions to change. So that works, right? Now if I were to do the same thing, only I have to change 0 to 1, 1 to 0. Now that will, you know what, I have it properly written so that I don't mess up stuff. If I put it here this way, now you see, again we have the sum of first, that is 1 and 4, that's 5, 2 and 5 it's 7, 3 and 6 is 9. So I hope this concept is important, is clear, because it's very important in the future. Now all the kind of, this is what we call reduction operators, and there are many of them. For example, sum, mean, prod, that is the product of the elements, minimum, maximum, argmin, argmax. So all these kind of different things are there. We are going to take a, you know nice look into this whole thing. Okay, so coming to mean, let's say let's do some mean would be basic, simple thing, coming here, blah. Okay, mean could not infer outside, input must be floating or complex. So let's put it into a floating points. Okay, mean, you got the mean, right? Not a biggie. Then again, let's do this again. What we're doing is along the columns. So mean of each row, as I said, along the columns, mean first row, it will be its mean will be taken, and which is basically 2, and this mean we take is basically 5. Okay, you can use it. This one also have the same parameters, keep, dim, and all that. It's gonna be the same. Let's see the another one. Prod of all elements, basic product of every element. If you want to see, it also has the same arguments, keep dimensionality is also there. You can check it out. You can just hover over this one and you can see all the and even the examples that you can find. So there are random numbers you want to put along one, means it will do the product of these two, then these two, and return 4 values out of it. That's fine. Coming to the next one, min. Okay, I'm telling you this because I think these are used mostly rather than other ones. So I'm just putting all of them together. Okay, you know what? I'm gonna keep this one as the default. I'm gonna delete this too and keep this one since sorry, this one as a default one, and do this. What happened? Please look up dimension by. Okay, seem to have some kind of a problem. Okay, let's debug. Let's try to debug this thing, right? That's the whole point of this live stream. Where is the problem coming in? Max dim equals to none. Okay, I don't think that's even a parameter. Let's try this. Okay, I don't think it's gonna do. Um, such indexing. It does not do that. Actually, if the main value has not defined. Oh, that's fine. That's fine. Value is not defined. That's fine. That's fine. Okay. Okay. This was working before. This seems to have some kind of problem. I am not able to fix. That I will be able to fix soon. Iteration over a 0D tensor. How is that a 0D tensor? Zero D tensor. It's supposed to be 6 and 5. It's supposed to tell you the dimensions actually. Hmm. Seem to be some kind of a change in the. Let's try this one out. Let's comment this thing out and try the other one. Yeah, other one seemed to work. Okay. Oh, okay, okay, okay. I think I got the problem here. Basically, the problem that coming here is we don't have that kind of a. Just it just gives out the value. It does not give out these things. It just gives the value. Okay. Hmm. So basically telling the value which is the maximum value in the whole tensor. That's the first function. Then maximum along a specific dimension. As I said, if I'm going along the columns, so which one is the maximum along and 3 and this one is 6, so 3 and 6. And it also, and one more thing, I think this also tells you the index at which the maximum is. So you see the for maximum each row is 3 and 6, and it's also telling you index of the row. So it's 2 and 2. What it means is the first row, go in the first row and look at the second. Basically it's 0 1 2, right? So if I were to plot it down here, it will be like 1 2. Oh, sorry, it's got some kind of a glitch. It's fine. I can okay. So it's like 1 2 3 4 5 6. So this is 0 1 2 0 1 2. From if I were to think of this as two different arrays, you know. So go into the first one, first arrow, and check the second element. Just go into second and check the second element. That will give you the maximum. So it will be the thing with minimum for along the rows. Same will apply for max. All you have to change is here is from max to min, and you will get the answers. Now coming to the next one. This is interesting. Okay. Now what are argmin? Argmin is basically telling you at what index are all the maximum or minimum. In this case, argmin is used. So which index would have the minimum value? That's all it gives. Okay. In this case, it's in the 0th index. What if I were to put here -1, -1? So it says 5. So now why is it 5? Pretty simple, right? One. So it's basically some values here. -1 in this case. Okay. So 0 1 2 3 4 5. So that's why it's 5. It was 0. If it were this, it will be 2 or something. So it's giving the minimum value by flattening it. That's what it means. So what is making it doing is taking all the elements, putting into a single array. If I were to put all this array 1 2 3 4 5 and -1, this is what it's doing, and it's assigning a number 1 2 0 1 2 3 4 5 and telling you the number. That's it. Basically flattening it and telling you the number if you are using argmin. But you have again the dimensionality thing, right? That can be used to actually specifically find what's the minimum value, where is the minimum value in the whole array. So for example, in this one, if you go along the columns, for the first one, it would be the first one. It's smaller. Okay, I hope that made sense. So is with the columns. I don't think I need to reiterate on that. uh, argmax, same thing, telling you the maximum ones. So I hope all that made sense, and let's move on to do some linear algebra. Right, now matrix multiplication is something that we all know, right? How can you do matrix multiplication in this? Now, there are many methods to do matrix multiplication, and this is one of them. Okay, uh, sorry. So you have matrix number one, matrix number two, you do a multiplication, you can directly use this function. This is also a way to do it. Okay, for example, if I take this and put it here and do it, it will give the same answer that is given here, right? It's an operator that Python has. I don't think it's a tensor operation at this point. uh, Maybe its project does that dynamically, converts them into a tensor, but yeah, even Python has the same operator. And what else? This is matrix multiplication. I hope you know what matrix multiplication is. Is basically one more thing I would like to talk about this multiplication actually. Maybe the way to visualize it. So dot product, right? Dot product. Let's start from here. Let's clean this up. Clean this up. Let's start from dot product, right? Say dot product. Now what is dot product? Pretty simple stuff. You have one vector 1 2 3, and you have another vector that is, again, let's say 0 1 2. A dot product between them is basically taking all the elements, the its corresponding element in this function, and multiplying them. So 0 into 1 and 2 into 1 and 3 into 2, and then adding them. That's it. So you see, it's 0 plus 2 plus 6, which will give you 8. So now there's a way to represent it, and that's pretty simple, which says 1 2 3, and then you take here 0 1 2. Now why do we represent this? Because this multiplication can be like this is multiplying with this, and 1 into 0, then add with this into this, plus add 2 into 1, so is 3 into 2. This is one way to represent this. Okay, now this one's dimension is basically, there's 1 rows and 3 columns. Here it's 3 rows and 1 column, right? If that makes sense. And it's also called a scalar product, because when you do dot product of any two vectors, it will give you out a scalar value, as you can see here. So when you do, and basic one more rule of doing this is, the column of the first vector or matrix, whatever, should be equal to the row of the second vector or matrix. Cool. Now coming to matrix, this was 2 vectors, right? So let's get to matrix and how does that work. So if you have a matrix of 1 2 3 4, and you have another matrix, the same 0 1 2 3, cool, I guess that makes sense. Now it can be broken down like this, 1 2 0 2. Next one will be 1 2 1 3. Another one would be 3 4 0 2. 3 4 1 3. Now this will become the resultant. Now this is 2 by 2. This is also 2 by 2. The resultant will also be a 2 by 2 matrix. And this is the 2 by 2 matrix. So what it does is, it's the matrix multiplication would be like doing n number of dot products. N number of, in the sense, the number of rows will define the n. Basically here we are doing 2 dot products, right? Then this one and the fast way to do it, if that makes sense. Okay, for example, if we had a situation, okay, the situation is simple. If we had a matrix like this, 1 2 3 4 5 6, and one big matrix like this. Hmm? So it's basically doing n dot products, this by this, this by this, and this by this. Again, the n dot products at the same time, and the resultant would be, this is 3 into 2, this is 3 into 1, and resultant would be, okay, there needs to be, okay, we cannot do this because the rows, as I said, the column of the first matrix should be equal to the row of the first matrix. So if it cannot be 2, it can only be, let's do this as 2. Instead of this, what we can do here is we can just write like this, 3 and 2. Now it works. So we have n dot products. It can be thought, matrix multiplication can be thought as n dot products at once. If we can do that, it will eventually become 3 comma 1. So basically there will be 3 values like this. This one, this one, this one, whatever value here is. So you got the dot product of this one with this one with this, with single operation. That is how I think about matrix multiplication. Okay, yeah. So let's go. Now there are things like inverses and what inverses are, what determinants are. Let's see what determinants is, just so you have an idea. Sorry. This is a determinant. Determinant, we all know what are. We have studied in high school. I am not going in to the depth of it. Basically, you multiply this one and subtract this one. That's all. Okay. Coming to the next one, trace. Trace is another one which is like the addition of the diagonals. Right? So if you add diagonals, it will be 5. 1 plus 4, that's 5. Trace is then. SVD is a little higher, so I'm not starting with that. SVD is basically a singular value decomposition. We can go into that later, I guess, and how it works and all. Eigenvalues, eigenvectors, very important. I think I should do a video on this one too, explaining these linear algebraic terms and why it's needed. Okay, seems to have. Okay, it should have this linear algebra right here. It wants this term inside here. Unexpected eigenvalues keyword. I don't think it's needed. Directly decompose it. Right, there we go. We have the matrix, their eigenvalues and the eigenvectors. See, it's a complex. This one is actually having complex eigenvalues and eigenvectors. That's pretty cool. Okay, it's float. It already converted the whole thing into a float, right? That's pretty cool. Because of this, okay, I haven't told you what this is. Basically, it defines what kind of tensor you want. You can add in the floats here, right? Or you can define it like this. Why I want D type to be a float 16, float 64, or even there's a big float, I suppose. There is also int. Int also is there. Okay. All Let's solve a linear system, right? Which is so prevalent in mathematics. We have it all the time. We see it all the time in the. What is a linear system? Okay. Let's start. What is a linear system? Now you have a linear system. Let's say you have equation 3x plus 2y equals to 7. And the other is 4x minus 5y equals to minus 11. How would you solve that? I want the value of x and y. Now this can be solved using simple substitution, right? Or we can use linear algebra to solve this. And that is where all these knowledge of matrix multiplication and all that stuff would come in. And here we are. Let's do this. So it can be represented as 3 comma 2, the coefficients. Okay, the coefficients are represented here, minus 5, and the values can be represented as x comma y, and then this is the other vector. Okay, so essentially what we have is x and y, and now I want to find their values. Now there are many ways to do this. Actually, you can do row elimination, column elimination, and get the values, or you can just take this thing and do an inverse of that and multiply it with this one. That also works. So basically we're trying to find the value of x and y, right? And that could be easily done using this simple method called solve. So your a is the matrix, and D is this. So you can call it, this one is A, this is the big A, and this is the B, this is the X, which we are supposed to find, and I can solve it. So AX equals to B, which is exactly what we have written here, and this is printed. So you have the value of X and you have the value of Y. Cool. I hope that is clear. Now, okay. Now we can do stuff like, doing eigenvalue and eigenvectors. They are mostly used in like PCAs, like, principal component analysis, where it's used for dimensionality reductions. So projected data and all that, we can come into that later, I suppose. Okay. We are going to jump into another one of the most, I guess probably this is 80% of the work that you're going to do with working with tensor. That is, now we are going to tensor manipulation, in the sense reshaping, transposing it, squeezing it and squeezing it. What they mean, I will tell you. And what our view, how can I view the whole tensor in a very different format than I have right now. So all these very important part coming up. Okay, so let's start with reshape. You have a tensor that right now, what you have here is a 2D tensor, right? A 2D tensor. Now 2D tensor can be, now the shape of the 2D tensor is, if I even show you the shape right now. Okay, I can put in the shape, print x dot shape. Okay, so I can find the shape of that, and then I can also do instead with that, I will also try to shape dot shape. Okay, and here we go. So you see the shape of the first matrix was actually 3 comma 2. There are 3 columns and 3 rows and 2 columns, but I reshaped this matrix into 2 by 3, and you see the resultant is 2 by 3. It's very important. Reshapes are used all the time. Now there's many ways to do the same thing. Okay, now let's go to higher dimensions. We haven't worked with 3D anymore, right? So here we will talk about 3D and working with 3Ds and all that stuff. Okay, so let's go here, paste it, and okay, so you have here a 3D vector of a shape is 2 comma 3 comma 4. So how I created it, basically a range prints out all the values from 0 to 24, and simply I'm doing reshape it in 2 comma 3 comma 4. So it created 2 3 comma 4 matrices, right? Okay, cool. Then now let's do some operations on this. Now this operation will be used a lot, like a lot. Let's say we want to reshape into a 1D tensor. You can 1D tensor, very easy. Okay, if this value is literally magic in PyTorch, where you put -1 into it, it does all the remaining calculation for you. Okay, it will see the number of elements that are in the matrix or the tensor, and it will automatically adjust it for the tensor that you're trying to build. So in simple word, if I just run this one, it will directly create a 1D tensor with literally 24 values inside them. Okay, we're gonna do one more of that so that you have understanding. And this is the second one, if you see. And if I do, if I run this one, so here, what it's doing is, give me a second, give me a, okay, sorry for that. Yeah. So coming to, so what it did was create, okay, so here what we do is it's 2 comma minus 1. What does that mean? I want two rows. That's all I'm telling you. Now you calculate the number of elements in the columns all by yourself. I don't want to care about that. Take all the elements that are there. I want the rest of them. You do all the calculation. I don't care about that. That is what essentially it means if you see this one. Okay. Coming to the next one. Let's do one more of that. Better. It looks so much better than this one. Okay. Now, here you see, I want a 3D tensor. Okay. So it says 2 and minus 1 and 1. So you are given two parameters and just added minus 1 in one of the dimensions. It will do all the calculation for you and directly do the created tensor for you. That's how simple is that. I want one element. Okay. I want one column. That's what it says. And it did all that stuff for you. I think it's really cool. And PyTorch. So is with this one. Let's do this one. Let's basically the same thing. Okay. Now we change something else. We put minus 1 here. We got another dimension here. So let's see. This one. Okay. I guess this is something I was working on. You have another X and you're changing, you want 4 columns. Okay, 4 columns are given. Calculate the number of rows. I don't care. According to the number of elements. Just do that for me. Now that is all minus ones. Now you can also use general like this. You want a 2y. One thing you have to make sure when you are giving actual values. Now the number of elements where in the original tensors was 24. So you have to make sure that it stays 24. It's 2y 12 is 24. If I put 11, it will throw an error because number of C invalid because there are 24 inputs. So I have to give in 12, or I can also give in, let's say 24, right? It can also be like 6 comma 4, 24. That's fine. That's fine. Okay, I guess I have nailed this topic. Reshape as well, but there is another function for transport itself, so why not just use that, right? uh Expected tensor. Okay, I think we're changing the tensor right here or something. Okay, I guess this one does not work. Let's try this one. Yep. Okay. Okay, something interesting. You have the x was, it looked like this, right? X looked like this. X is this. You want to transpose it 1 comma 0 comma 1. You want to swap the dimensions of 0 and 1 for, in this case, that dimensions. So now this is a 3D tensor. You would understand. Okay, transpose mostly happens in simple words in matrix 0 1 0 1 2, 3. So if I do a transpose of this, the row became columns and column became row. So 0, 1 and 2 and 3. This is how it's gonna be, transpose of any simple 2D matrix. But what we have here is a 3D matrix, right? We have 3D matrix that has a dimension of 2 comma 3 comma 4, right? I want, what it's saying is, this is a 0th dimension, this is the 1, this is the 2. I want to swap these two. I want to swap between them. I want to do a transpose between these two. Okay, so if you see what's happening here is, if I swap these two guys, what's gonna be the resultant? 3 comma 2 comma 4, right? So they're gonna be 3 in the third one. So let's see, what do we have? 3 of them? Yes, we have 1, 2, 3 of them. Then 2 rows and 4 columns. We see 2 rows and then 4 columns are there. So that's how easy it is. Now this is a very simple idea of doing transpose.t. What it does is, it does the transformation along the last 2 columns only. So this was the original one. This was the original one, and let's try this out. The original one was there, so let's 2 comma 3 comma 4. What it does, it does the transpose between the last 2 columns only. So it will be 2 comma 4 comma 3. Now let's check it out. So it says it's 2. Okay, did I miss something? So this is 4 comma 3 comma 2. 4 comma 3 comma 2. It's changed into 4 comma 3 comma 2. Now there's a okay, I'm sorry about that. It does it change between the last 2 of them, 4 comma, so it was, if it was a bigger, it will just take the first one and last one and then do a transpose, if it was 3D or 4D, in that sense. Okay, so you have to be very clear on what dimension what operations are doing, because every single one is very different than each other. So it's very important that you understand this. And now transpose can be done, as I said, with any kind of a thing. Okay, already I guess I have shown you, so let's go to the next one. Permute. Permute is another function that does the same thing as transpose, so let's go to one of the most important topic, and then I will end the whole thing, and I guess the other things can be done later. Next is squeeze and unsqueeze. What is squeeze and unsqueeze? Okay, it's probably the most interesting among all the other ones. um, it adds in and removes some dimension out of something. Okay, for example, you have x that looks like this, and what it's saying is, I want to unsqueeze at second position. What it means is, so you have this whole thing right here. Let's remove this, don't need this. Okay. So you have this whole thing, it's 0, 1, 2. I want to add one dimension into the second position, so it will result in a 2 comma 3 comma 1 comma 4. That's all it's doing. Okay, if you see this now, if I add this one, it will become like, if I see the shape, see, this one was, if you see the shape of the original one, this was 2 comma 3 comma 4, and this changed to, so what it does is, unsqueeze means making it bigger, right? So we are adding a dimension into the whole thing. Numbers aren't changed anyway, it's 1, so there's no problem with that. Now we can do one more thing, that is called squeezing. Squeezing is making it smaller. So I can add this to any dimensions, right? If I put 0, here, it will add into the first one. So you see the first one is added. Okay, now I can take the same thing, put it here, and say squeeze. Okay, squeeze at 0. Now 0th is there isn't any what do you say, dimensions. For example, I will put this one. Okay, this one here, we added this one into the original one. So if you want to remove these ones from the dimension, all I have to do is do a squeeze on the originally changed one. So if I do this, we will change the whole thing again and make it into the original one. Okay. So you have a tensor that has a lot of redundant dimensions, like one comma one comma one, and then the actual thing happens, right? It does not make sense. Practically also thinking, if you have a image and it has like 1 comma 3 comma 28 comma 28, right? It's like basically one image. So why do you want to put that? So if you want to remove that one from that, so you can just do squeeze and unsqueeze, and squeeze up probably used a lot in the whole process that we are gonna deal with. uh, I hope this is understood. Okay, now let's do some crazy thing like a very big vector and do some squeeze and unsqueeze operations to see how it works. Okay, yeah, so this is a big vector. It says 2 comma 1 comma 3 comma 1 comma 4. It's a big vector, right? If I were to print it, it would look something like this, with a lot of redundant stuff which has nothing to do. Okay, and even understanding this just by looking at the tensor, it's very hard. What is the dimension? There are few ways that I do it. Maybe I will share it in the next videos. But yeah, so let's do squeeze on this. If I directly do squeeze on it without any dimensions, what it does, it takes all the ones out, put it out. So if I see now the shape of this one, check the shape. So it removed all the ones. See, the shape was, it has a lot of ones inside them, right? It removed all the ones. Now if I want to squeeze along along the first one, so it will just remove it from the first one, as I have already shown you this one before, right? So that's all good. Coming to the next one, unsqueeze, squeeze. Let's take the squeezed one and add again. We will taking this one that's been squeezed, no, this one that's been squeezed, and add a dimension to the first one. So if you see dot shape, you will find it, we added this one into this one. Okay, yeah, now there can be you can also do like a nesting of squeeze and unsqueeze, as I can say, like you're adding in this one, then adding in the third one, whatever, then you got this. So now I guess you are able to understand what all these operations are and how they work, squeezing and squeezing and all that. So I'm going to stop the stream right now. Next stream we are going to talk about concatenation and stacking, how that things work, and probably the most important part in all of this is broadcasting, which we will discuss the next time, basic slicing and stuff. Okay, and few tensor to tensor operations like where and all that, where and gather, scattered. These are few other functions. Then we will talk about a little bit about distributions that you can like you can create random numbers, and these random numbers can be like sampled from some distribution. There can be like a uniform distribution or a standard normal distribution, or a distribution that is has your own specified. Talk about that. uh, any suggestions you have, you let me know what kind of videos you want. If you want me to go and actually start explaining you the linear algebra and calculus, which I will do eventually as we go on, but we want a separate video on that, why it works, how it works, maybe the mathematics a little bit more. So you can let me know, and let's see how these things roll out. Okay, so thank you for joining.